Okay, we're going to solve now a problem of spherical shell and see what the electric field is outside the shell and inside the shell. In the problem, I drew the shell with a certain thickness here, but what I mean is that it has no thickness. I just put a certain thickness so you can see it, to illustrate what it looks like. Okay, so just imagine that there has no thickness at all. We want to find the electric field for R bigger than A and for R less than A. So as we do with any problem that has some kind of symmetry, we need to know what the direction of the electric field is at some point outside the shell. So let's go to this point in space and ask what direction should the electric field point at this point. So we'll do the same kind of symmetry argument. Let's assume that the electric field does not point on the radial direction. We rotate the shell and the vector, everything, by 180 degrees around this axis. It turns out that the shell itself doesn't change because a spherical shell stays the same when it rotates around 180 degrees about the central axis, but the vector has rotated and has changed direction. So this cannot be the case. You cannot get the same charge producing a different electric field vector. So the only conclusion is that the electric field must be pointing radially outwards. And remember that this is not a circle, it's a spherical shell, it's a sphere, it's a three-dimensional shape. Here, we're just drawing a cross-section of it. Okay, so now we know that the electric field vector is radially outward everywhere. So what shape Gaussian surface would you choose and where would you put it? Because remember, when we solve Gauss's law, we want to get rid of this dot product. Same thing we did for the other problems. You take a spherical Gaussian surface because the area vector and electric field vector at every single point on the spherical surface will be in the same direction, and the angle will be 0. And that's the way you can get rid of the dot product. So we start with Gauss's law, and E dot dA becomes E dA cosine theta, but theta is equal to 0 for all the elements. So cosine 0 is 1, and that means that this dot product has now disappeared. The next argument is a symmetry argument. The electric field vector, if you evaluate it at any point on the surface of the spherical Gaussian surface. Because of symmetry, when you go around the sphere, everything looks exactly the same. There's no way for the magnitude of the electric field to change as you go from point to point. Of course, the direction is different, but the magnitude remains the same. So E has a magnitude, as a number, it goes out of the integration. You get E times integration of dA. Integration of dA is just the total area of the sphere that has a radius r, which is 4 pi r squared. You get the left-hand side of Gauss's law. For any spherical shape, it always boils down to E times the area. Now, what about the right-hand side? What's the right-hand side of Gauss's law? How much charge is inside this blue Gaussian sphere? Obviously, the total charge of the shell is inside because the whole shell is inside the sphere, so you get Q. So this is what the final relationship would be, and we can rearrange to get the electric field. Then we show that the electric field is Q over 4 pi epsilon naught r squared, which is KEQ over r squared, which is the same as the electric field due to a point charge. The interesting part and the surprising part maybe is how to get and what the electric field value is inside the shell. So if you have R here at this point, for instance, or at this point, any point inside the shell where R is less than A, what would the electric field look like? So first, what shape of Gaussian surface would you choose? We'll choose a sphere that has a radius R less than A for the same reason as we did before. There's spherical symmetry. Now, I'm not saying that there is an electric field here, but imagine that there is an electric field. If there is one, the nice thing that will happen is that E dotted into the area will become E times E dA, cosine 0 is 1, so we got rid of the dot product. And if there is an electric field, I'm not saying there is one, but if there is an electric field, it will have the same value everywhere on this spherical surface, so I could take it outside of the integration. So the left-hand side of Gauss's law is the same as it always is, E times 4 pi r squared. Okay, but what about the right-hand side? What is the total charge inside this Gaussian surface? As you see in the drawing, there's no charge inside the Gaussian surface. So that means that Q inside is 0. If you plug Q inside to be 0 over here, we get that E times a finite value is 0. It means that the electric field is exactly equal to 0 when R is less than A. So we get a very strange result, that the electric field inside the spherical shell is exactly equal to 0 at every single point, not just at the center, but at this point, at any point you choose inside this shell, the electric field is 0. And outside, it behaves like a point charge. Now, this might be kind of the typical question that is asked, or is a comment that we get at this point is, if you put your point over here, say, people would say, well, the charge here is closer to the point, and the charge here is farther away from the point, so shouldn't the electric field here have a net value and it shouldn't be 0? This is the argument that people usually give. If you want to look at the problem in more detail, of course, you could apply Coulomb's law. And to apply Coulomb's law, remember, this is a spherical shell, it's not a circle. So it's a spherical shell. I just drew it as a circle, but you have to imagine this is a sphere. You would have to cut up your spherical shell into small elements of charge. You would have to get the electric field vector due to each element of charge. You would have to add over the whole shell, add the electric field vectors due to every single part of the whole shell. When you do that, the charges that are on this half, or not half, on this side of this point upwards, on this spherical cap, these charges produce electric field vectors that point downward, and yes, they are large in magnitude because the charge is close to them. But the thing is that there is much more charge that is on the bottom of this spherical cap that is producing an electric field upwards. So there are so many more vectors, electric field vectors, due to the charge that's on this side. It's true that the charge here is much farther away than to point P than the charge here is, but there are so many more vectors. If you calculate the problem exactly and you add all these vectors properly using Coulomb's law, you will exactly find that the total electric field is equal to 0. So this is something you can actually prove using Coulomb's law. If you want, take it as a challenge and actually try and prove it. And if you want to come and discuss it with me, we can try to solve it together.